So I'm going to just talk in some more detail today on virtualization and network disaggregation with SPDK. We've got our notices and disclaimers slide. I think I've learned today the only thing longer than this slide are delays on American Airlines. So agenda, I'm going to talk about how SPDK implements storage virtualization. I'm going to go through some backgrounds on VirtIO, vhost, QEMU to give you a little bit of background on how those work and actually how the efficiencies, how we realize the efficiencies with SPDK. I'm going to go into more detail on logical volumes. So talking a little bit more about the underpinnings from a software perspective and some of the features that we've been developing there. Then going to go through some use cases that we've developed where we've built some systems up that combine these two virtualization and disaggregation concepts. And then we'll follow that up with some performance data. OK, so starting out, storage virtualization with SPDK. So I'm sure most of you are familiar with QEMU and VirtIO. For those that aren't, VirtIO is a para-virtualized driver specification. So there's actually there's a spec for this. It has a lot of common underpinnings that are used for doing a lot of different types of device emulation. They use this for networking, for block storage, either VirtIO block or VirtIO SCSI, and it's being extended to a lot of different device types as well. And so the key part here is that you've got the. Let's see, do I have a laser pointer? I do not have a laser pointer. You've got your guest VM, which is running the VirtIO drivers. In the hypervisor, then you've got the backend and you've got the device emulation here. And so this works very, very well, but there are some overheads that come from this when you're talking about I/O. And these apply, here I'm focusing on storage, but a lot of this applies to networking as well. And I'm going to talk a little bit about how a lot of the things that we're doing for storage, we've actually sort of stolen from what they've done on the networking side, which has allowed us to make these fairly quickly. So when we look at the I/O overheads of the common QEMU model, we've got several big areas of latency here. A big one is when the guest actually rings that doorbell to notify the hypervisor or whatever that device backend is. There's a VM exit there. That VM exit it's expensive. We've got a context switch that then comes into play because we have to wake an I/O thread now in the hypervisor to go process that I/O. And then at some point, we're going to translate that into something that's going to go to an NVMe SSD. And we're going to have a system call there. We're also going to have an interrupt from the device once that's completed. And so Anu, and I mean, you've heard a lot of the discussion, SPDK, DPDK in the past, and we want to avoid those device interrupts and that overhead.
You called VirtIO a para-virtualized system specification, driver specification. What do you mean by that, para-virtualized?
Well, I guess when I say para-virtualized, I mean it's something where the the guest VM, it sees that it looks like a PCI device. It's not really a PCI device. So it's it's emulated.
Yeah, but para-virtualized is the virtualization of an idealized device, not the virtualization of an actual device.
Exactly.
So if you have a VMware guest, you can choose the para-virtualized network driver or the emulated Intel E1000 network driver.
Exactly. Yep. Yeah. Okay, so the idea behind vhost is that you basically create a separate process to do this I/O processing. So here we're starting up a vhost target. Now the interesting thing here is that this can be either kernel or user space. In fact, this whole vhost concept originally started in the kernel. DPDK was the first to basically move this target up into user space. The idea is that now you move these backend drivers, you move the device emulation over to this vhost target, and then the name vhost comes in here because this is the protocol. This is how QEMU tells the vhost target about the VM. So The process here is when you want to, before you create a VM, you're going to allocate some storage or maybe a network device. You're going to communicate that with the vhost target. The vhost target's going to create a Unix domain socket, and then QEMU's going to connect to that, tell the vhost target about the memory that's been allocated to the guest VM, the vert queues, where those vert queues are in memory. And the other nice thing about this is as we have more and more guest VMs on the system, we can have one I/O process to handle all of them, right? Here, when you have this, you've got this code running for every VM. And so this gives us a lot of opportunities to consolidate, be able to handle many I/Os from many VMs at once, and we can get a lot better CPU efficiency through the polling method because we can pull many VMs on one CPU core. So now, why does this work better with when we have a user space vhost process? So we're polling. So we can actually tell the guest VM, the VirtIO has hints that we can tell the guest, when you put the I/O into the queue, don't ring the doorbell. So then we avoid that entire VM exit. That's actually a huge source of the software overhead. We're polling, so there's no extra context switch. And then in the SPDK vhost process, we're doing all the submissions and completions in user space. It's all polled, so we remove that overhead as well. One thing to note here is that the guest VM is not polling, so we still have to send a interrupt back to the guest, and so that does incur a system call. But other than that, we're able to do everything completely in user space in the SPDK vhost target. Any questions on this? This is just kind of showing a little bit more about what we've done here. So, I talked a little bit about how DPDK has enabled this for networking. We've been able to reuse a lot of that code. SPDK, when we started this project, we called it DPDK for storage, and we still rely on DPDK for a lot of the underpinnings, for accessing devices from user space, allocating huge memory. There's a lot of stuff that DPDK does that we just use rather than inventing it ourselves. And so this is one of those cases. You can see here we've got the Unix domain socket. That's how we pass this control information about where the guest resources are. And then we've got this event file descriptor, which is used for the vhost target to send interrupts back to the guest. But then everything else is basically done through shared memory. So the SPDK vhost target can directly access the memory of the VM. Nice fancy animations here. Okay, so next, SPDK logical volumes. So this comes up a lot. How do you share SSDs in user space? One of the drawbacks of this model is when you have a target and you want to be able to share a device with with multiple entities, the SSD is basically owned by one process. When you're talking about vhost, you're typically not going to assign a whole SSD to one VM, right, and then virtualize it. You might as well just directly assign the SSD to the guest. So SRIOV, I think we're going to start seeing SSDs that have more SRIOV-like capabilities to where you can partition some amount of storage, some number of queues, create a virtual function out of that, and be able to assign that to a guest. But those SSDs are not prevalent yet. The mainstream SSDs don't have that. And this also precludes features such as like clones and snapshots and thin provisioning. These are things that typically are going to be difficult to implement in an SRIOV SSD. So if you're working with the Linux kernel, you're going to use LVM, right? But we've moved the block stack up into user space, so using LVM is pretty much a non-starter. So we really need to have a user space solution to be able to do logical volumes, and that's what I'm going to talk about next here is, what's that? Blob store. Yeah, so let me talk a little bit about
That's kind of awesome.
blob store and logical volumes and how they kind of layer on top of each other. So as we kind of came, as we started, talking about this, we wanted to have a solution that we could use for very targeted storage use cases. So, like Anu was talking about blobfs that we use for RoxyB. This is not intended to be a full replacement for ext4 or ZFS or ButterFS or any of those. This is specifically, designed like for RoxyB. It's append only, relatively large files. You don't have a lot of directory hierarchies. For logical volumes, it's basically, again, very large blobs on disk. And so we're really trying to make this minimal so that the code is not overly complicated, but actually make blobs so that it can fit multiple use cases. So at a high level, the chunks of data are called blobs. And blobs consist of one or more clusters. Typically, these are going to be on the order of many megabytes of storage. This is not designed for a lot of very, very small blobs.
Blob is just such an attractive name.
What's that?
Blob is just such an attractive name.
Blob is, yes, it's a very attractive.
It's very descriptive.
Yes.
And it will generate enough of an emotional response that this will become an attention-grabbing thing, whether it's whether people like technology or not. It'll get people to talk about it. It'll be good.
So it's completely asynchronous. So just like the rest of the SPDK in these user space pulled node models, everything is, there's no blocking, there's no queuing, there's no waiting. So when you issue read and write operations to the blob store, you provide a callback function. At some point later, you're going to get a callback once that operation is complete. Fully parallel, so there's no locks in the I/O path. And then one of the key things is from a metadata perspective is we've designed this around the NVMe atomicity guarantee. So all writes are 4K atomic. So that means that a blob, it's always going to consume at least one 4K metadata page. We do not have one metadata page shared across multiple blobs. This really allows us to take advantage of some of those atomicity guarantees and ensure that even in power fail situations that we can recover all the data correctly.
So with no locks in your metadata handling paths, I mean, how does this maintain the metadata consistency and acidity and all that stuff?
Yeah, so we actually we use some clever techniques where we have message passing built in. So basically, we have, when you create a blob store, when you initialize it or load it for the first time, we keep track of the threads that are being used by the application. And so we will actually send messages to one thread. So there's one thread in the system in the blob store that will do all the metadata operations. So if, for example, the simple case is when you create a blob. So we always say we have some restrictions on the API. For example, if I'm going to create a blob, I have to create the blob on the same thread that you initialized the blob store on or you loaded the blob store on. So that case is fairly easy. We know that's all going to happen on the same thread. The trickier part now is now that we've implemented things like thin provisioning and clones and snapshots, now you could have some other thread that's doing an I/O and it's doing a write operation to a cluster that hasn't been allocated. Now he has to go do some metadata stuff. And so what that thread does then is he'll actually send a message to that first thread we talked about. It'll do all the operations for the metadata. He'll send a message back once it's done, and then that initial thread can complete. And so that's the approach we've taken, is really to try to, rather than doing a lot of complex locking, we do high-speed message passing to that one core, and then it can take care of making sure that the metadata page.
So you sort of single thread your metadata options in order to eliminate locks effectively.
Yep. And we found with the pulled node architecture that sending these events, it's a very it's pretty low latency,
right.
And it reduces the complexity of the software actually quite a bit. Okay, so when we kind of look at this logically in SPDK, so I mean everything is built around BDEVs, right? So you've got You have your NVMe namespace, which is a block device. You put a blob store on top of it. And then we have this layering. And when we talk about logical volumes, it's effectively blob store, but we add a few extra attributes on top of it. So we have UUID so that we can uniquely identify not only the logical volume store itself, but also each of the logical volumes. Meaning that if you were to move this logical volume store from one system to another, you could still identify it in the new system. And then we still have friendly names as well. So similar to like what you have with LVM, so you don't have to type out a 36-character string to identify it. You can save a name with it. The name gets saved in the metadata as well. And then we've added support for thin provisioning and clones and snapshots. So workloads like VDI can work here as well, where you can have a common image, take a snapshot of it, and then create multiple clones, and they'll share that backing store. And so then in the end here, now you see we've taken this one NVMe namespace, and now we can create many block devices on top of that, and we can expose them as NVMe over Fabric namespaces, as vhost SCSI LUNs, vhost block devices, et cetera.
And the metadata for that NVMe SSD blob store and vol store is sitting on the NVMe?
It is. Yeah. Yeah. Okay, so I'm not going to go into a ton of detail on the NVMe over Fabric's target. I'd be happy to. I think we're doing lunch after this. If people want to talk more about NVMe over Fabrics, we can certainly do that. But what we've done in this setup is we've taken the SPDK vhost technology, we've taken our NVMe driver and logical volumes, but then we've sort of like split them out. And so we've got. I'm going to show a diagram here in a little bit about how we've done that. But basically, we've got two different systems. They're both dual socket, Xeon Platinum with lots of physical cores. We have 4 of the Optane SSDs in each system. And then these systems are connected by a Mellanox ConnectX-4 100 gig NIC. And so kind of, building up here, what we're looking at is, so we're kind of starting out, we've got our Optane SSDs, then we're building logical volumes on top of each of these. And then we're starting a number of VMs on this target. And then each of those is going to access both 2 local and then also 2 remote logical volumes. And then for purposes of this exercise, we're actually launching 8 VMs, and so they're going to consume all the logical volumes that are on these Optane SSDs. What's that? Okay, so I'm going to show some performance data here. Okay, so first, like looking at the very low level, looking at the NVMe overhead, and I think a lot of people have seen charts like this before. We're basically comparing what you get with an Optane SSD using the Linux kernel block layer with libaio, and I'll call out here in a second why I'm specifically talking about that versus SPDK. And so you can really see what the software overhead is here of the block layer. There's a lot of questions is like, what's the proper way to really measure this on Linux? You can use libaio. There's also pvsync2, which does some polling or hybrid polling inside the kernel. We feel like for these SPDK comparisons, using libaio, it is higher overhead in the kernel, but pvsync2 really only works for QDepth1. And for a lot of these target applications, you're going to have higher QDepths. These SPDK numbers, as far as the software overhead, they stay consistent as you ramp up the QDepth. But for the Linux kernel with pvsync2, if you want to do QDepth2, now you've got to create a second thread to do that extra I/O. If you want to do QDepth4, well, the pvsync2, it only allows you to do 1 I/O at a time.
Oh, okay.
So you certainly, these numbers do come down quite a bit. They probably come down to the more 10 to 12 microsecond range if you're using pvsync2. But this kind of, just want to explain a little bit about why we've used libaio for this comparison. And so what we've done here is, that setup I was describing earlier, what we're doing here is we're doing queue depth 1. We're running I/O from inside of the guest VM to one of the remote logical volumes. And so what we're doing here is we're showing the full end-to-end latency. So you're going from the VM, it's coming into the vhost target, it's got to go over NVMe over fabrics, it's going to go through the logical volume layer, and then it's going to go down to the NVMe SSD. Then it's going to go, data's going to go all the way back. And so you can, what we've tried to do here is kind of break this out to be able to show like each step of the way, what's the relative amount of overhead, the amount of time that each part of that takes. And so here we can see, this is basically the data we were just looking at. This is just access to the NVMe SSD. We've got the disaggregation part here. So this is effectively the NVMe over fabrics overhead. This is both submitting the I/O and handling the completion of it on the initiator side, and then also on the target side, receiving the I/O and sending the completion back to the initiator. So you can see this is, I mean, this is huge. And the benefit here is that with SPDK now, we're saving time at both the initiator and the target side with this polled mode model. And then here you can see on the virtualization side, this is primarily the VM exit. So we're getting rid of the VM exit. That cuts out quite a bit of time as well. So you can see with the, with the standard Linux kernel, you're approaching about 60 microseconds of overhead. With SPDK, it's a little bit over 20. So that's a huge difference. And so you can see for this Optane media, this next generation media, this is really the approach that you need to go, right? That 10 microsecond latency is great, but when you add all this overhead, you've lost some of that those advantages, and that's why we think that for these NVMe over Fabric use cases, I think this is why you're seeing a lot of people starting to pick up SPDK.
No, I mean, aside from the excited murmurs and ahs you're hearing, this is actually pretty epic. I mean, it's because a lot of us hoped that we would see stuff like this. I mean, because to be honest with you, DBK shocked the hell out of most of us, right? I mean, the fact that there was that much cruft to remove,
right.
and that was really kind of shocking. And so it was kind of like it was kind of a dare to dream that there would be that much benefit to still see in the storage layer, and it's like this is pretty cool.
Yeah, we think so too.
And this is just a software latency. So on top of this is actually a device latency, which is on the order of 6 or 7 microseconds by itself, right?
Right, exactly. Yeah, some part of this is the media latency on the SSD, and then in here,
some part of that software latency that's sitting there at 7.3 is media latency.
A good chunk of this is the media latency.
That is the media latency.
Yeah. I mean, so we've. So
why would that change between the Linux kernel and the SPDK? Because if it's media latency, be media latency regardless.
It layers because it's
and we could. You're right. I mean, we're kind of showing
double
overall.
The
this
media
includes
latency.
Software and the media latency. So you're right. We could break this out and say, let's say it's. I'm just going to throw a number out there. I don't have the. Let's say 6.5 microseconds is the media. You could break this out and then basically show. Well, here we've got a few hundred microseconds of software.
So it's really a combination of media latency and software latency.
It is, yeah. This is the actual measured, this is the total measured time from the guest VM of when it submitted the I/O to when it got the completion. So, but you're right. I mean, even this part here with the disaggregation, I mean, there's some amount of, you've got to send the data over the wire. It's got to go through the NIC. I mean, there's some overheads there too that you just can't get rid of in host software.
Hey, Jim, real quick.
Yeah.
There's a question came in via Twitter over here.
Okay.
Jay asked, what are the configuration requirements on the host, particularly in the SR-IOV environments for accessing NVMe controllers inside the SPDK environment?
Yeah, so from an SR-IOV perspective, if you have DPDK and SPDK, they work just as well with physical functions as they do with virtual functions. So if you had an SR-IOV enabled SSD and you assigned a virtual function to a guest VM, that guest VM could run the SPDK NVMe driver there, and it would work. It would work just as if you were using a physical function on the host. Is that?
That's cool.
I'll assume.
Okay.
He'll comment on it.
Okay,
and
perfect.
I'll throw it out there again.
Okay, and then here what we're doing is now we're kind of using that full setup that I was showing earlier, where we've got the 8 different VMs. It's accessing local storage and remote storage. And we're running like a Cassandra-like I/O workload. So it's doing random reads and writes, medium, queue depth 8, a bunch of mixed block sizes. And what we're doing is we're restricting the number of cores that both solutions are using. So on the VM host side, we're limiting the number of cores that are doing I/O processing. On that second node, we're reducing the number of cores that are running the NVMe over Fabrics target. And so, this is a lot of times when we talk about SPDK, we talk about performance, but a lot of times it's efficiency as well, right? If you throw enough cores at it, you can get the performance, but really you want to be using those cores to run more VMs. You don't want to be using those cores to do I/O processing. And so, based on those restrictions, we can see, here with the kernel-based solution, we're 340 to 350K IOPS, where with SPDK, we're above 1.2 million. And then you kind of see the similar drop in the latency.
Hey, Jim, real quick. He came back in with a follow-up question.
Okay, perfect.
He says, does SPDK then handle the PCIe PF and VF functions?
SPDK handle the... Okay, so some of this probably depends a little bit on the usage model. So personally, I have not used an NVMe SSD with SRIOV today, but the way that I would see people using that in the future is you would use the Linux kernel NVMe driver to control the physical function in the host. You would use that to allocate the virtual function, so allocate the space, allocate the queues, and then that virtual function would be using SPDK but up in the guest. So that's how I kind of envision this getting broken out. And I think that's going to actually be really useful down the road for cases where you have an NVMe SSD and you want to use some portion of it as a boot volume, which means the Linux kernel has to own it, and the rest of it you want to use accelerated with SPDK.
Okay.
So some of the numbers we were seeing earlier were 500,000 roughly IOs per second per SSD. These are 16 SSD systems.
Yeah.
You expect to see 8 million IOPS, and we're only seeing 1.2.
Yeah, so there's a few things here. So one is we're limiting the number of cores. So if we threw more cores at it, we'd probably get more throughput.
How many cores are you limiting it to?
What's that?
How many cores did you limit it to?
So we actually limited this to, I believe we used 2 cores on each system to do I/O processing. So we could put
a 56-core system, you limited it to 2 cores.
No, but IO distribution says 2 vhost cores for SPDK and kernel.
Yeah, so we've got 2 vhost. I know it's like 2-point font down here. You got 2 vhost cores down here for the kernel, and then we're using the rest of the cores for QEMU.
I think it's more that you limited the queue depth to 8.
What? I'm sorry?
I think it's more that you limited the queue depth to 8.
Yeah,
The numbers we were looking at yesterday were 64.
What we've seen with the Optane SSDs is that you can hit that max IOPS at a relatively low queue depth. Certainly with NAND, queue depth 8, you would not get anywhere close to that max. On Optane, you can get there relatively quickly. So to answer your question, if we threw more cores at it, both of these numbers would probably go up. There's some other limits we would hit as far as the 100 gig link. That's a really good question. I'd really be curious to, I need to follow up with our performance guys, because 100 gig link is going to get you about, 12, maybe 10 gigabytes per second. And we're probably getting relatively close to that max here, because you look at these random IOs, and some of those IOs are fairly large. So, it's a good question. Probably some things we could tweak and throw more cores. It's kind of always that trade-off. Like how many...
but the point of the slide is the relative, not the absolute anyway.
It is.
It would be much
But I
more
think,
relatively higher if it was going 8 million IOPS. And
Yeah, but
it's always fun to see bigger numbers.
yeah.
I'm just trying to figure out where the overhead is. I mean, obviously SPDK is trying to reduce the overhead. That's in Linux, and certainly it did, but yeah, okay.
Yeah.
Jim, real quick, we got
Okay.
another question here.
Yep.
Are there any numbers indicating the CPU utilization for SPDK versus non-SPDK? Lower latency is good, but how many CPU cycles do you need to pay for pooling?
That's an excellent question. So, yeah, if your application only requires 10, 20,000 IOPS, SPDK is not. I mean, that's not what it's meant for, because you're always going to be burning a core. So, you know, what we've been able to measure is, you know, yeah, with the Xeon core with the Linux kernel, you're typically somewhere in the 400 to 500K IOPS. So for a lot of these target applications that are trying to require, you know, multi-million, SPDK is definitely the way to go there. From a CPU cycle perspective, we've measured with SPDK, it costs about 500 nanoseconds of software overhead per I/O. So there's definitely some kind of back of the napkin calculations you have to do to decide whether you know, the investment and the cores make sense. I will say that one of the things we're actively working on in SPDK is for our target applications is the ability to dynamically turn cores on and off, right? So when you have a very high workload, you're spreading stuff out to more cores so that you can hit the throughput that you want. But then when you detect that those polling cores aren't really doing any work, you can funnel that stuff to another core and you can shut that core down. Or you can use some of the technology where you can, you know, like speed step, where you can turn the frequency up or down based on the workload. And so it's an excellent question, and I mean, that's something that we're working on. We don't have solutions for it yet, but that's definitely one of the factors to take a look at.
Thank you.